Welcome back. So we have taken a low mass star from birth to the main sequence, and then from the main sequence to its ultimate demise as a white dwarf. Let's do the same thing for high mass stars and think about how they're different. Unlike the sun, a high mass star, meaning one that has 8 solar masses and above, will be hot enough to burn helium into something heavier in its core. And in fact, it will be, carbon into something. The sun is also able to burn helium. The high mass stars will be able to burn carbon into something else. They will get hot enough to burn heavier elements. Specifically, if they can get to 600 million Kelvin, they can burn carbon into things like neon and magnesium. If they can get to 1.2 billion Kelvin, they can burn neon into something heavier. If they get to 1.5 billion Kelvin, they can burn oxygen into something heavier, which is interesting because oxygen actually has a lower atomic number than neon neon does. Actually, if you look at a periodic table, and this is something we probably should do, let me share my periodic table with you. Here it is. So just to recap, the sun is currently burning hydrogen into helium, the two lightest elements in existence. The sun will eventually be able to burn helium into beryllium, and in beryllium, which will decay back into helium, but before it does, it can, if it's smashed into another one, it can get to carbon, and there it will stay. Carbon can burn into neon and magnesium and oxygen. Interestingly, oxygen you'd think would be the next easiest to burn, but it's not. Neon is actually easier to burn than oxygen is. At 1.2 billion Kelvin, oxygen burns at 1.5 billion Kelvin, and finally, things like silicon and magnesium can burn into heavier things as well. But it's helpful to see the periodic table, I think, so you can sort of see where these elements lie and what they are. Okay, let's go back to our slide, and we're thinking about all these elements burning, here is, again, these numbers aren't important to memorize or to know really, but I think it's important for you to see them and see how this works. So here is the example of a 25 solar mass star, which is a very massive star. A 10 solar mass stars, the numbers will be different. The temperatures and densities will be a bit lower. The durations will be a little longer. Higher mass stars, these numbers will be higher and the durations will be longer. But you get the idea. Let's go through the processes for a 25 solar mass star and think about the conditions at the center of that star when each of these things actually happens. So, for instance, hydrogen burning happens at about 40 million Kelvin, 4 times 10 to the 7 Kelvin. Remember, the sun has an internal temperature of about 10 million Kelvin. So this is about 4 times hotter than the sun is, even at the same stage where it's burning hydrogen and helium. Obviously, as you go up in each successive element that you burn is at a much higher temperature. So 200 million Kelvin for helium, 600 million Kelvin for carbon for this particular star, 1.2 billion Kelvin for neon, over 2 billion Kelvin by the time you get down to the silicon. And the densities get extraordinary. These density is fairly low, relatively low at 5,000 kilograms per cubic meter, still way denser than we'd have around here. But it goes way up from there, right? Helium burning goes up by more than a factor of 100 in the density in the center of that star. Goes up by a factor of more than 100 again when you burn carbon. When you're burning neon, this density is more dense than the white dwarf we calculated its density of in the previous lecture video. Oxygen, 10 to the 10. This is 10 times the density of that white dwarf we considered. Silicon burning as well. These are extraordinarily large numbers, both in terms of the temperature and the density at which these things are happening. But the interesting thing I want to point out here now is the duration. How long do you think each of these successive phases of burning happens? And it does happen in succession. It burns hydrogen in the core, it runs out of hydrogen, then burns helium in the core and hydrogen in a shell. By the time it gets down to oxygen burning, you're burning all of these elements and shells around it. We'll look at an image in the next slide. But how long do each of these last for it being the source in the center, which is powering and holding up the star? Let's go through it for a 25 solar mass star. Bring back my, oh, no, that's not what I wanted. Let me bring back my low scale whiteboard. That's the one. So I've copied this table over to my actual low-tech whiteboard, and I'm going to start writing these durations on one at a time. How long? Well, let me tell you the first one. Helium burning. This is at a very high mass star. Does not take anywhere near as long as the sun does, because it's so much hotter and denser. It goes through it much faster. This we expect to be about 7 million years, about 10 to the 6 years. Again, for comparison, the sun has this phase will last about 10 billion years, 10 to the 10 years, a much longer number. Okay, but as I said, from low mass stars, helium gives you a lot less energy than hydrogen did. And so it can survive much less time with helium being the energy source than it did with hydrogen being the energy source. How long do you think that is? You can make a guess. Helium burning will last at the center of our star for about 5 times 10 to the 5 years, less than 1 million years for helium burning to be the source of energy at the center of our star, about 500,000 years. How about carbon burning? What do you think? How long is carbon burning going to last? It gets silly in a hurry now. Carbon burning only lasts about 600 years for the star. That's it. 600. This is now, time scales that you can almost wrap your brain around. Neon burning. How long do you think neon can support the star? Neon burning. Each of these successive layers lasts a shorter amount of time, and it gets short rather dramatically. 1 year. About a year is all that neon can support the star for. How about oxygen? 6 months. Silicon burning, by the time silicon is burning at the center of your star, you can only support it with silicon burning for about a single day. So that's it. The game is over at that point. So that's the example of this 25 solar mass star. Let's go back to our slides. Great, here we are. So that's silicon burning. Those are the durations. A huge range in different time scales, and silicon being by far the smallest. Okay, so when silicon is actually run out, after that day happens, what is it gonna look like? Well, silicon burns into iron. So I like to, high mass stars at the ends of their lives are like ogres. And ogres are like onions. They've all got layers. And so this is what the layers of a high mass star at the end of its life look like. If it's spent the day burning silicon, you now get an ash at the center of your star, which is pure iron, basically. You'll get a silicon burning shell on top of that. You'll get an oxygen burning shell on top of that. You'll get a neon burning shell on top of that. Carbon and oxygen, carbon burning shell, helium burning shell, hydrogen burning shell. All of these layers successfully from the inside out are burning successively lighter elements as you go from the interior to the exterior. This is the onion shell model of what the end of one of these stars' lives might look like at the very center of that star. And so that's kind of at least a cartoon of what it will look like. What does it look like on the HR diagram? Where are these stars moving? Well, post-main sequence looks a lot like pre-main sequence. If you remember, low mass stars, they came down and changed a lot in luminosity and not much in temperature. The same thing happens in reverse. They change a lot in luminosity and not much in temperature as they move up towards the giant phase. These high mass stars are exactly the opposite. Again, the pre-main sequence, they moved almost straight left, changing in temperature but not much in luminosity. When they evolve off the main sequence, they're doing exactly the opposite. They are changing, getting very cool in temperature and not changing much in luminosity at all. So that's not, the details of this aren't important. I just did want to point out that post-main sequence evolution looks a lot like pre-main sequence evolution for both low mass stars and high mass stars. Although you'll see some differences. These high mass stars, at least some of these, say 10-ish to 12-ish to 15-ish solar mass stars, can actually loop back and forth several times at the top of the HR diagram as they go through these successive layers of burning. Helium, so running out of hydrogen, maybe moving over here, maybe starting helium burning, maybe moving back here, maybe moving back once you run out of helium, and then it can sort of move back and forth on the top of the HR diagram as it moves through these various stages of evolution. Okay, so what are these high mass stars doing? What do they look like? They're extremely violent at the surface. These things are so luminous intrinsically that they are not all that well bound, and they're often losing mass at a prodigious rate at the at their surfaces. So here's an example. Here's a nice image of the star-forming region, the Carina Nebula. This is one of the largest star-forming regions in the galaxy. You can see lots of cool things going on. You've got a cluster of very young, bright, massive stars here. You've got some things going on over here. Lots of very dense molecular clouds. Lots of emission nebula where it's been heated up by these massive bright stars. Some dense knots of regions potentially where more stars are forming as we speak. A very rich and energetic and interesting region of the sky. I want, though, to zoom in on this guy right over here on the left side of this picture. This doesn't look like much here, but it is one of the most massive stars in the galaxy. It's one of the most massive stars that we know of. We can only kind of estimate how massive it is, but we think that it's probably like 100 times more massive than the sun. We don't think it's possible to make a star that's much bigger than this. So if we zoom in on this thing, what does it look like? This is a fascinating picture. Check this out. This is what it looks like. It kind of looks like, reminiscent, if you think back to the planetary nebula video or images that I showed you at the end of class on Tuesday, it looks a lot like this. Again, this is the star in the middle, and it's obscured by this huge amount of stuff that's been pouring out of the star for many years. And it's not coming off uniformly. It's coming off, again, in sort of two nozzled jets. One lobe behind us and one lobe pointing towards us. And so this is what a high mass star like, well, this is the star Eta Carina. Eta because it's the, I don't know what number Eta is in the Greek alphabet, but they often will name stars according to their brightness within a constellation. So Carina is a southern constellation. That star isn't actually visible from Geneseo. Alpha Carina would be the brightest star in the constellation Carina. Beta Carina, Gamma, Delta, etc. I think Eta might be next. I'm not quite sure. Anyway, it is that number bright star in the constellation Carina, but it goes through outbursts, and sometimes it's a lot brighter than others. And it went through a particularly violent outburst recently, where it was the brightest star in the southern sky for a while. But then it settled back down, and it seems to be doing more normal bright star, massive star things. Okay, great. We will stop there, and I will think we'll come back in the next video and think about what happens after you get to iron in your core. It turns out it's bad and explosive and exciting things. So stay tuned for that.